Today is Friday, the 3rd of April. So we are going to attempt this outline today. And I really want to start with the soil-plant-atmosphere continuum and then move into the components of plant water potential. Now, we teach whole classes just on plant water stress and plant water potential. So in this lecture and the next one, we're going to go over the highlights of plant water potential, the basic elements. Over at the screen, you can tell we're getting close to the end because we have, after the lecture today, we will have covered every single equation on the front page of the book. Remember our flux equation, and this is the flux equation for photosynthesis, Ci and Ca, conductance, and the flux in photosynthesis. If this was Hi and Ha, this would be the flux of water vapor out of the stomates. And if we're talking about liquid water, it's the gradient of water potential over resistance in transpiration. So it's still the gradient over the resistance that determines the flux. I think the last time I had written delta P over here, and that was confusing. This is the correct way. It's the gradient in liquid water is measured in megapascals. So we slide this down just a bit, and here's total water potential is two components, and we'll get to this in a minute. In the book, I mentioned previously that chapter 7 is transport and partitioning, which directly relates to Phloem Transport and harvest index, but sugar movement in the phloem is driven by a pressure gradient. It's still liquid, and it's maple syrup moving along in the phloem, but it's still driven by this megapascal gradient. So it's important to understand plant water potential at a fundamental level before we can think about sugar movement in the phloem going to fruits of the plants. So chapter 8 is plant water relations, and these two chapters are intimately related, and we'll really talk about plant water relations first. Once again, this stuff is covered in detail in every single plant physiology textbook ever written, at least ever written in the last 50 years. You don't need the newest version, because they all, as new versions come out, what happens is the graphics often get better. But the fundamental physical principles of mass and energy transport have not changed for at least 50 years, maybe 100 years. But it's you can tell how important it is because it's in every book. So let's do this soil-plant-atmosphere continuum again. We had it drawn over here, and to get it really clear, we're going to have brown roots down here. Now let's draw the whole plant. Here's the plant, our simplified plant, way up here. One leaf and one oversized stomate in that leaf. So we've got, oh, now I should put this in blue because it's water, but remember from last time, soil water is, and this is in psi, I'm going to abbreviate. Field capacity is minus 0.03, and permanent wilting point is minus 1.5. These are units of megapascals. All right. If we take an average of -1. A nice round number. This is a nice starting point for water in the soil. It's not soaking wet, it's not completely dry, it's just -1. This water moves to the root surfaces, up through the xylem, up through the xylem, up. It's getting sucked up to the top, goes to here, and then, and I'm going to put a squiggly line here, because that's vapor, water vapor. Changes from liquid to water, it evaporates right there. All that cooling we talked about, that's happening right there inside the leaf, and then the vapor leaves into the air. This is the soil plant atmosphere continuum. And as a rule of thumb, and we'll put numbers on all this stuff, as a rule of thumb, we'll consider it starting at 1, right here. Now, there's a real simple model to help understand this movement of water vapor, because this would happen in a dead plant. This is not, there's no ATPs involved in this. It's just the movement of water up out of the soil. In fact, it happens right here too. Happens by evaporation just from the soil surface. So the same principles apply. It all follows the latent heat of evaporation. But here's a model of how plants work. It's a universal, super simple model. This is it's a Buchner funnel that has a porous surface in it. And I took a Sharpie and made it black, because that's more of the radiation exchange of a plant leaf. And you get this whole thing full of water. So that's all water, so this surface stays wet. And this is a model for transpiration. And in fact, people use this. They put tick marks on here, and they say, "Ooh, a centimeter of water evaporated, then I better irrigate a centimeter." This is a commercially used device. We've had a gauge in here. I don't know where it is right at the moment. But it's a commercial gauge to do exactly what we've got in this jar. The water has to be continuous up here so it can keep wicking up. If you get an air bubble in here, the whole thing stops. So, and here's a little baby version of this, same thing. And if we sat these on a balance, we could calculate the evapotranspiration rate of this laboratory. But this is a wonderfully simple thing. Now, trees are big, so they have to wick this up 1 meter, 10 meters in the case of a tall tree, but they still wick it up to the surface, and it still evaporates out the top. And here's the key point. It's sucked all along the way, sucked up, sucked out of the soil, suck, up to the top, changed to gas, and the process keeps happening. This is the fundamental concept. When we get to Phloem transport, there's suction in this system in a dead plant, but plants are not dead. They have turgor potential, and they're under pressure, and turgor is what expands leaves. If this whole thing was a suction, what force would ever cause cell enlargement? We couldn't have cell enlargement. That's a pressure. So we got suction to move water, but simultaneously, we've got to have pressure in the cells. So to understand plant water potential, when we do delta MPa, megapascals, that can be either negative or positive, and here's the best way to think about that. Move our demo over here, go to this, let's see, put this on it's good on a black surface. Here's a syringe. If I pull back, we have suction, a certain force of suction. If I push, it's a pressure. So you can see if I wanted to transfer water from this, we might have -1 megapascals. And then over here, if I release it at the exact same time, it would be +1. So we just moved water with the combination of suction and pressure. So this stuff gets tricky, as you will see, because it's mathematics with a lot of negative numbers. And you think, okay, I can do addition and subtraction, but you got to practice to get the math right with all the negative numbers. Let's put, so we can put some numbers on this. If it's -1 to be sucked up into the plant, right here in the plant, it can be -1.5 megapascals. This is more negative, so water flows downhill. I think that's to get a PhD in plumbing. That's one of the things you got to know. Water flows downhill. But in this case, tricky, because water is flowing downhill, but it's going up, because it's going to more negative, getting sucked over here. Now it goes up. Now we might be -1.7 in the xylem, in the stem, still being drawn up. Leaves, I'm going to draw this big, -2. This is all good, but look, the leaves have to be -2 to get water from down here. Now you see the importance of irrigation. If they have to start at 1.5 down here, this gets a lot more negative up here. There is a famous, excuse me, a famous diagram of this over time as these plants get more and more negative water potential. Let me draw this on the board. I can send the actual diagram, but I think it'll be more clear if I just draw it. Here is days, and this goes up to multiple days, 0, 1, 2, 3, 4 days, and here is megapascals. And we're going to go, in this graph, we're going to start at 0. You can already see negative numbers. Graphs start at 0 down here. We're going to start at 0 on the top. This we just irrigated. And we're going to do 3 lines on this. The first one is the soil. And we're going to start at -0.03. And as this soil dries out, this is a bit accelerated, but to show the principle, the soil is going to look like this. Each day, and right here, is -1.5 megapascals. So what we've done is, this is like a plant in a container where it runs out of water fast, or maybe your lawn grass where it runs out of water very fast in 4 days. There's the soil. What happens to the water potential in the roots? And let's see, what are we going to do for roots? Different color, we'll do those in orange. Roots, right here, they get a little more negative in the middle of the day because there's a big flux of water. Then night comes and they recover. So they go back up. Now, this is important. Here's day 1. This is midnight. MDNT, midnight. They recover at midnight, even though they had some suction in the day, because of all this big flux of transpiration sucking the water. What happens to the leaves? Shown in green. The leaves had to get more negative in the day to keep up. They had to suck harder. So wow, even though it's at field capacity, already the leaves are way more negative than the field capacity. What happens on the second day? The system's running out of water. Now the roots there's two, they get more negative. And because the water's harder to get, they had to pull harder. This is like a giant Slurpee with a lot of crushed ice. And when it's full of this, it's easy to get the water out of it, and then it gets less and less, and you're going at the end, and it's almost out of water. It's harder and harder to get the water out of the crushed ice. That's what's going on down here. So they got more negative. What happens to the leaves? Ooh, more negative. But they still recover at night. And this is important that they recover at night. The plant's fully hydrated, charged up, almost like a battery. It's a good analogy for this as a battery, but it can still recover at night. And technically, if we do night, we should show some period where the night is, all the lines are together up here. Next day, whoa, same thing with the roots. Lower. Now look at the leaves. They're recovered at night. Now the leaves get like this. Aha! The leaves are starting to get close to minus 1.5 megapascals, even though the soil is not that close yet. But if these are all sunny days, the leaves have to pull really hard. And look what happens on the third day. Roots again, like that. Now, here's the leaves. They would normally go like that, but this is so much suction, they stop. They can't pull any harder, and this happens right around 1.5 megapascals. And when they stop, the plant wilts. It can't pull any harder. The plant starts to wilt. And typically, plants will start to wilt when the soil gets down to around minus 1.5. Now, the reason this is not permanent, it's not death, they can recover, and it's the approximate wilting point. Some plants have bigger root systems than others. Some plants can suck harder than others. But you get the idea. This part of the plant is a lot more negative than the soil. And how much more negative it is depends on the humidity of the air, and it depends on how sunny it is. If it's a huge evaporative demand, we have to have an enormous flux of water. We could draw multiple arrows up here to emphasize all the water we got to get up there on a hot day. And if the soil is partly dry, the resistance of the phloem is fixed by the diameter of the phloem. We got to have a huge delta megapascals in order to provide the water to the top. The most famous example I can think of to show this is the common garden vegetable, squash. Now, if you have a garden and you grow squash, especially in Utah, you can walk out and look at your squash plant and it's wilted. I grow a lot of squash. Happens every summer, all the time. And what do you mean? It's wilted. I just irrigated yesterday. This is what is called physiological drought. And it comes from the water cannot get to the leaves fast enough. If the plant has to, they just wilt, they can't keep up. And it's real common in squash. It's water stress, premature water stress. Now what happens later in the afternoon, the sun goes down, the squash recovers fine. There's plenty of water in the root zone. It just couldn't get there fast enough in the middle of the day. So the next time you see squash, look for that. It only happens when the plant's big, and squash can get some big leaves, and so it has huge water demands. But squash doesn't have the xylem capacity to deliver the water fast enough to the leaves, so it limits the growth. There is a very famous diagram about what I have just drawn up there. I give you one of those. And I'm going to show it here because I'll send you this as a handout. Here it is. Now, this is just the diagram. What you really need is the interpretation that I just gave you. But this diagram shows up in Introduction to Soil Science books. It shows up in a lot of different books. But it's this plant that's starting to wilt down in here as the water gets less and less. Now let's talk about the components of water potential. And, no, let me hold off on that. Let me put in here, before I talk about this, let me talk about this part right here. All of this is pretty simple, and it's nice. It's integers, -1, -2. Leaves can get to -3. There's some species that can get to -5 megapascals in the leaves. It's amazing. They can become really, really negative. And other species, like say squash, they can't hardly even get to -2 because they can't get water out of the soil. But remember how our flux of transpiration equals delta H. Now I'm going to write this over resistance. It's delta, but it's also delta H times stomatal conductance. But the delta H, which is HI minus HA, this has units of kilopascals. And this, that we touched on last time, is megapascals. How can we have water moving through the soil plant atmosphere continuum? These are all negative numbers. If it's negative, mega, and now it goes to kilo, this is 1,000 times less suction than this. But as I said last time, this is vapor. Water vapor, not liquid water. Here is how you convert between them. This is a famous equation. I'm not sure this equation has a name. I should look that up. We should see if this has a name. Psi, which is, and W is water. This is all psi W, total water potential, equals RT, and that's in Kelvin. So this is the ideal gas law constant, R, temperature in Kelvin, divided by, let me make sure I got the same symbol, VW, and this is the molar volume of water. So this is going to look like the ideal gas law equation. These are pretty close to constants. Take this times our old friend, the natural log of the relative humidity. Not absolute humidity, this is relative humidity. So now, if we get humidity of the air in percent, we know this number. It's the log of that number times this. Now we know this in megapascals. So we can, and I'll give you a handout of this, but let me work it out right here. This is how we go from humidity, which we can convert to HA, to megapascals. Let's work an example, but very quick. R times Kelvin over the molar volume of water is, make sure I don't put any wrong numbers up here. R over VW times temperature Kelvin times the log of the humidity. This number right here is 0.46. The molar volume of water is 0.018. And I'm not going to go into the derivation, but this is 0.46. Temperature in Kelvin, let's assume 300, which is slightly warm, 27 Celsius. So this is a pretty constant, times the log. Now, this has to be the decimal fraction. So what if this is 100%? Here, 100%, this is the log of 1. The log of 1 is 0. So the water potential at 100% humidity is 0. That's, no water can move. It's saturated air, saturated water. There'd be no evaporation. But if we put in, right here, let me put this in a different color for emphasis. What if we have 99% humidity? Natural log of 0.99 times 300 times 0.46. This number comes out to be minus 1.35 megapascals. Mega. Wow. Log of 0.99 is something like 0.0. It's a tiny number. This is times. At 99% humidity, we are almost at permanent wilting point. That is just amazing. That's why plants can't get water out of the air, except if it's fog. They got to get liquid water out of the soil, because even at 99% humidity. Now, in the soil, if it's dry soil, permanent wilting point 1.5, the humidity in the soil at equilibrium is about 99%. What if we went to 98%? We'll drop the humidity way down, 98%, 0.98. Well, guess what? This goes to minus 2.72, and all our plants are dead at 98% humidity. That shows you this nonlinear relationship between humidity and water potential. If we do 50% humidity, which is around here, that's pretty humid. Now I'm out of room. I'll put it up here. 50% humidity, RH, equals minus 93.6 megapascals. Now talk about the movement of water. Goes from 1 to 1.5 to 2, and here's the stomates controlling where it goes to minus 100 at a modest humidity. This is why stomates are so important. This water, this gas comes pouring out of here, and these poor stomates all day long are trying to regulate this so the plant doesn't dry out and wilt. But they got to stay open to get CO2. And this is the reason, it's this equation converting gas and humidity of the air to water potential. I'll give you a handout on this that shows it. This is also in every plant physiology textbook if you want to look at that. All right. How about components? I don't think we talk about components of plant water potential much in more introductory classes until you get to plant physiology. But let me start with an example before you even talk about components. Here is a beaker, just like this beaker here, with water in it. Only this beaker, we're going to put a semi-permeable membrane. Now this membrane could be something like plastic wrap, real thin, but it's a semi-permeable, and it's going to separate this. Now we're going to start with this, so it's right in the middle, and we start with water. And that's deionized water, both sides equal. Now we put in one side, and we put in Na plus Cl, regular table salt. We just sprinkle some in. Doesn't take much. It's just a fraction of a teaspoon per liter. And that salt goes into solution in here. What happens to the water on the two sides of this beaker? The salt ions bind water. It slows the activity of the water down so that it binds some of the water. This is again like the third graders, only now there's the third graders and I don't know, they got to carry a big backpack. Like that's the salt molecules slowing them down. So when the molecules get slowed down by binding to the salt, these molecules over here, which aren't slowed down by any salt, they move over here. So there's a movement of water from the pure water side to the salt water side, and look what happens. This goes up, and this goes down. The water didn't change. It just gets drawn over here. This is the fundamental principle of water, components of water potential. Water moves downhill where there's more salt, because there's more binding. This would happen if we put soil particles in here too. Something to bind the water. Now the soil would not stay in solution, it'd fall out, but the water would get bound to the tiny particles of soil, and the same thing would happen. So this concept leads to the components of water potential, and right here, psi W, this is 0, and this is 0. This is before we put any salt in this. Now we go to putting salt here, and the water moves, but we've got to have a component of water potential that draws it over. So the first step of this is psi water equals psi solute potential plus psi turgor potential. When we put salt in here, if we put enough in, this might go to -1. A negative was 0 on one side, so now we'd have 0 on this side and -1, and the water moved over there. But look, we made a column of water. It doesn't keep moving forever. It raised this water, so now there's a pressure potential pushing back that way because one side has more water than the other. So it's pressurized, and that's turgor. And turgor is always a positive number. So the math gets really easy. The whole system is still at 0. But one side is 0, and the other side is -1 plus 1 equals 0. So the turgor went to +1, pushed back, equalized this number, and this is what equilibrium. It would this would keep happening until it's got to steady state, and it would get to steady state at this value. This is the fundamental concept of plant water potential that turgor pressurizes things. Now, what if we took this beaker, let's see if I can draw this on here, and we didn't make it open on the top, but we put a lid right here. And we put salt in one side. Same thing happens, only this sides get pressurized. And when it gets pressurized, that's turgor, and that's what causes cell growth. The more positive this number, the faster plants grow, because it's the pressure causing cell expansion. So the bottom line is plants have to accumulate solutes so that they can have pressure. If plants didn't accumulate solutes, the whole system would be zero. There'd be no water movement, there'd be no turgor potential, they wouldn't grow. These are the first two components of this, and they're the two primary components in plants. What about soil? I said if we put soil in here, it'd do the same thing. When this water binds to particles in a soil, like our Slurpee that we're trying to suck water out of, solute is ions, and when it's bound to particles of soil, it's psi matrix. And this is particles. Now, particles and ions do essentially the same thing, but these are not in solution. This is physical binding, and these are chemically bound. But they're both negative numbers. So in soil, it's mostly bound to the soil, and we suck it out of there. And once it gets inside plants, it's solute. Now, the solute has to be more negative than the matrix potential, so we get water. Water potential, this W is for water. W. This is the total, and this number is what determines delta P. This is always psi W. Now, these are the key components. The terminology can get a little sticky sometimes because in some cases you'll see people writing psi P for pressure. And that's fine. Maybe that's even more descriptive than turgor, but psi P and psi T are the same. And sometimes you see people writing psi T over here, only that doesn't mean turgor, that means total. So you just have to keep track. And people generally define what this means. But this is always called matrix. But pressure potential, and it might be more descriptive to say pressure and then total over here, but sometimes psi T means turgor, sometimes it means total. We got one more thing. What if we took this beaker and we made it, it's drawn in black, and here's our membrane in the middle, but we made it, how tall are trees? How tall are redwoods? 30, 40, let's say we got a 50-meter tall redwood tree. Would this change? If we kept putting salt in here, this goes up and up and up. It turns out it does by height, and that is the fourth and final component. Give myself every speck of room here. Psi, and this is often called Z, and this is gravitational. And this is how hard it is to suck water up to the top of tall places. And just, you know how in the energy balance we say we usually ignore photosynthesis and respiration? Well, we usually ignore gravitational. Because in a 1 or 2 meter tall plant, this is hundredths of a megapascal and we just ignore it. Now if we start studying redwood trees, now it starts to add up. But it's for typical crop plants that are less than 2 meters, this is such a tiny number that we don't worry about it compared to all these. So there's 1, 2, 3, 4 components that equal water potential. And just like energy balance, this has to balance. The math, these have to add up. Some positive numbers, some negative numbers. So we got plus a minus 1 and plus a plus 1. But this is the concept of plant water potential. Now, let me think about if there's what the next things I want to talk about. I don't have the equation with me right now, but I do have an example, and the next lecture I'll give you the equation. How much salt do we need to add to water to get to -1? This is really relevant here. We got to find more colors. Our planet is covered with water. We are not out of water on the planet Earth, not even close. 70% of the surface is the oceans. We have plenty of water. Can we irrigate with ocean water? No. Can we drink it and stay hydrated? No. What's the water potential of the ocean? And that is seawater and this is pretty constant all over the planet. I'm in the Arctic and the equator, really constant. Minus 2.4 megapascals. I'm gonna put that in a box. No wonder we can't water with seawater. It's well below permanent wilting point. And it's why we can drink seawater, but it won't hydrate us. It's too negative for us as well. But it's close. And there are some plants that can grow in seawater because they can get, well, down to -5. So mangrove trees grow in seawater. So they, even bound to here, they can grow. We have worked for 50 years to breed plants that we could grow on seawater. And we do have crop plants that can stay alive, but it is so much work for these plants to get more salty than seawater that the yields are terrible. We've not yet figured out how to do this. The only way we do it is desalinization. And we filter the water, take the ions out, and now we have good water, but that takes a lot of fossil fuels. So, but this is a key number when we think about the flux of water through this. Next time, and I think we'll stop here. Next time we'll talk about the amount of salt and how to calculate the megapascals of salinity based on the amount of salt. But I want to leave with one thing, and this will lead into next time. If we do a picture, xylem. Phloem. Now, you can prove you're an advanced plant science student. Which way do fluids move in the phloem? And hopefully 100% of people get this right. Up. Harder question. Which way do fluids move? Sorry, in the xylem, did I say phloem? Which way does water move in the xylem? Up. Period. Always up. from soil water to the top. Which way does solution, it's really water, move in the phloem? In a high school class, students would say, aha, moves down. In this class, partial credit, because phloem can move both ways. It can move up or down, depending on the gradients. Here's the $64,000 question that we'll talk about next time. How can we have two tubes right next to each other, and one's going up and one's going down, and there is no mechanical pump to push the fluids around? This all has to be done by chemistry, and it's one pump, it's moving up, and right next to it, it's going back down to the roots. How can that happen? That's what we'll talk about next Wednesday in class. Thanks.